Welcome everyone to the last session of our PDE seminar. And today is a great honor for me to introduce Professor Kaye. He is going to talk about the fibering method applied to the level sets of a family of functionals. Please go ahead.
Okay, thank you, Gabriele. So I will turn off my camera because I will be looking down to my iPad. So I prefer to close it. So, okay, it's a great pleasure for me to be here. I would like to thank Gabriele for the invitation. And I don't speak English very well, so I hope you can understand me. And if there is something fuzzy here, you can just stop me and ask. Okay. So I want to speak today about some techniques that have been developed in the recent years. So it's very new and very fresh. And so the title of my talk is the fibering method applied to the level sets of a family of functionals. And this is a joint work with Humberto Ramos, which is here with us, and Professor Gaetano Siciliano. So can you see my screen, right? It's okay here. Okay, so this is the plan for today. I will briefly introduce you the Nehari set. So just some definitions, and then I will try to connect the Nehari set with the fibering method of Porojaev. And then I will combine these two things here and speak a little bit about the technique introduced by Professor Yavidat, which is called nonlinear generalized relay quotient. And then I will try to show you how to apply some ideas related to this technique to the level sets of a family of functions. Okay? Okay, so let us start, and let me give you a definition of the Nehari set. So given a C1 functional, which I will call here phi, and it's defined on a reflexive Banach space, we have the following lemma, which is trivial, and it says that if you take any critical point of your functional, so here you can assume that u is not zero, then you can easily show by using the definition of Frechet derivative that phi prime of u applied to u is equal 0, right? So this is trivial. You just calculate this derivative in u to get this equality. Right? So a more interesting is the following. So instead of this, we want the converse of this result. And so to study this converse, let us introduce the Nehari set. Right? So the Nehari set is a subset of our Banach space. And so we take off the zero function or the zero element. And so u has to satisfy this equality here. So if you take a look in this lemma here, you see that every critical point of your functional has to belong, every non-zero critical point of your functional has to belong to this set, right? This set is called the Nehari set because it was introduced, or at least it was used to analyze some equations by this mathematician Nehari. Okay, so every critical point of our functional belongs to this set. So we now want to somehow of a converse result for this lemma. And the converse is given by this theorem here. So let us use this notation for the function of phi prime of u. So I will call it j of u. And let us assume for simplicity that j is C1. And moreover, let us assume that the derivative of j in u applied to u is non-zero. So with these two conditions here, we can conclude that the Nehari set is in fact a C1 manifold, and moreover, the Nehari set is a natural constraint to our function of phi. And by natural constraint here, I mean that if we restrict our functional to the Nehari set, and if we look for critical points of this restriction, then the critical points of the restriction are critical points in the whole space, right? So it's in fact a converse of this result here. We can look for critical points of phi restricted to n, and then find critical points of phi in the whole Banach space X. Okay. So the proof is very simple. In fact, it's a consequence of the implicit function theorem, and you can decompose your space by using the tangent plane of the Nehari set and the line which cross the Nehari set transversely. Now for that reason, you usually see the name for the set by Nehari manifold instead of Nehari set. So when phi satisfies these conditions, it is in fact a manifold and can be called Nehari manifold. But as we will see further on, in general, this set is not a manifold. So I prefer to call it here just Nehari set. Okay, so as I said before, it was used by Nehari in 59. And just to give you an example, let us consider this functional. So it's the squared norm. It's the Sobolev norm here to the power 2 and the Lebesgue norm here. So U is the standard Sobolev space. And if you apply the definition, you see readily that N is defined by this condition here. And a simple computation shows that, in fact, this condition is satisfied for this functional. And then this set here is, in fact, a manifold, which is called the Nehari manifold. So why do we care about the Nehari manifold? So for us, the main applications for us here is in elliptic PDEs. And we all know that the critical points of the energy function, in fact, are weak solutions of our PDE. So we want to understand and to analyze the Nehari manifold or the Nehari set in order to analyze, to study PDEs, in particular elliptic PDEs. Okay. So as I said before, in general, the Nehari set is not a manifold. So to understand this, let me introduce you some subsets of the Nehari set, which are defined by the following expressions. So the notation that I already introduced, we will always assume now that J is C1, and we can define any plus, any zero, and any minus as subsets of the Nehari set, for which we have this inequality. So plus is for positive, 0 is for the equality equals 0, and minus for negative. Okay, so in some sense, this is a natural definition, because if you look on the conditions of this result, you see here that we ask that this number is non-zero. So if it is non-zero, it can be positive or negative. And positive is here and negative is here. Right? And then applying this result, we can prove this one, which says that these sets are mutually disjoint, which is obvious. The union of these three sets is the whole Nehari manifold, which is obvious too. And by using the last result, we can prove that any plus and any minus are in fact C1 manifolds. And again, they are natural constraints to our function of phi, right? So because of this, we also call this set a Nehari manifold, and this one is also called a Nehari manifold. And in general, this one here is not a manifold, right? I say in general because depending on the situation, it can be a manifold, but in most of the applications, it is not a manifold. And in fact, this is the part of the Nehari set which gives us some trouble, right? So if you want to use, if you want to look for critical points of some function of phi over the Nehari set, we will have difficulties if this part of the Nehari set is not empty. So as we will see later, the main technique introduced by Professor Yavidat was to understand when this set here is empty or non-empty. Okay, so just to make things concrete, let me give you another application. You can consider this functional here, right? So it's the energy function associated to a concave-convex equation. So Q is bigger than 1 and less than 2, and P is bigger than 2 and subcritical. Right? So for this functional, you can calculate, it's not so hard to show that for each lambda positive, lambda is this parameter, we have that both n lambda plus and n lambda minus are non-empty. And you can also show that there exists a parameter, which I will call lambda star. This parameter is positive, and n lambda 0 is non-empty if is empty, yes, it's non-empty if and only if lambda is bigger than or equal to lambda star, right? So in some sense, if lambda belongs to this interval, is less than lambda star and positive, we can find critical points to phi lambda just by minimizing this functional here over n plus and n minus. And somehow this is easier in the sense that you can just use the direct method of the calculus of variations. So this was done, for example, in the paper of Yavidat. This theorem here was proven in the paper of Yavidat, and in a more general version, but not in this full interval, it was studied by Brau and Wu. Okay. So the main issue, if you want to study a functional like this, and if you want to study it over the Nehari set, is to understand when n lambda 0 is not empty. So if it is not empty, we can we study we have some good topological properties of the functional defined over these sets. But if it is empty, but if it is not empty, then we have some topological difficulties in order to study this function. Okay, so I will see me. I lost. Okay, it's here again. Okay, so I will speak more about this in the later on. Let me now just briefly say what is the fibering method and connect the fibering method with the Nehari set. So the fibering method was introduced by Porojaev, and in fact it has a more general form, but for our applications, let me consider this method in this form. So what we do is we do a fibration of our Banach space, and we take off the 0 point. And this fibration consists in, for each u of your Banach space, you consider the line that starts at 0 and goes and passes through the point u, right? And so you have now this line, and you can restrict your functional to this line, right? So when you restrict your function to this line, we now have a function which we will call phi u, and this is a functional which we study when we start to study mathematics, right? It's just a real function defined on the line. Okay, and this function, which is called the fiber, we can try to understand its graph and its properties. And there is a relation between the fiber and the Nehari set, which is given by this, right? So the relation is very simple. In terms of the fibers, you can show that the Nehari set, in fact, is the non-zero points of your space, which satisfies this equality here. So they are, one is a critical point for this fiber. And then you can also give now a geometric interpretation for the Nehari set n plus, n0, and n minus. So n plus, in fact, consists of the critical points of the fiber, which are local minimizers. N minus are the critical points, which are local maximizers. And N0 are the critical points which are degenerate. So it can be, for example, inflections. And here there are some pictures which says exactly this relation. So you have here the some part of the graph of the fiber, and it has a local minimizer here. Again, here we have an inflection point, and here a local maximizer. Okay, so the fiber binning method, it gives a more geometric flavor for the understanding of the Nehari set. Okay, so now let me introduce to you the method which was introduced by Yavidat in this paper of 2017. So the main question that Yavidat went to address in this set, in this paper, was the following. Right? So given a family of functionals phi lambda, so lambda is a real parameter, how to understand or how to determine if the Nehari set associated to this functional at the parameter lambda is the n0 is non-empty. Because if it's empty, we can somehow try to minimize phi lambda over the Nehari manifold or over n plus and n minus, and then you can find critical points. But if this set is non-empty, we have some difficulties to do this procedure, and then we have to avoid this situation. And so Yavidat answered this question for a very large class of functional. And the main idea, roughly speaking, was to do the following. So he considered the equation J lambda of u equals 0. And so by definition, if this equation is satisfied, we know that u belongs to the Nehari set. And now you look to this equation, and if possible, you write lambda equals lambda of u. Okay, for example, if you go back to this functional, right, you can calculate j of u for it, and which will be something similar to this one. And then you consider this equation. You can isolate lambda because this equation is linear lambda. So just isolate lambda and you get lambda of u, right? So if this is possible, you get this new functional, which depends on u, and now you can apply the fibering method of Porra-Jaev to this functional, right? And consider its fibers. So you fix some u in your space, consider the fiber associated to this functional, and here I draw a picture of this fiber. Right? So let us assume, for example, that the fiber associated to u with respect to this new functional lambda is given by this red curve here. So by a simple analysis, which I will not do here, you can prove this. Okay, so for example, if you take lambda 1 and consider the line which has height lambda 1, you see that you have this cross, which is transversal, right? It crosses transversal to the curve. And then you can prove that when the crossing is transversal, for example here, which is transversal too, if the cross is transversal, then we have this equivalence. So Ty, which is for this blue, which is T2 and T1, right? So the image of these points are lambda 1 or lambda 2, and they correspond exactly to points on the Nehari set, which does not belong to any zero. Right? So geometrically, you have that this is an equivalence. So each point that for which the cross is transversal, they have to belong or to any plus or to any minus. And this dependence will be given by this inclination. So it's positive, it can be 20 plus or 20 minus, and if it's negative, it will belong 20 plus or 20 minus. And you also may consider the crossing to be not transversal. So here you see that the tangent plane of the curve coincides with this line here. So in this case, you have here again a T3, right? And you can prove that, in fact, T3U has to belong to the Nehari set, and moreover, it has to belong to the N0. So this picture gives a full description for us to whether a point belongs or not belongs to N0. Okay, so after this, and now we have to put some hypotheses. So just to fix ideas, let us assume that all of these fibers here has just one critical point. For example, they could be all like this or all like this. And so if all of the fibers has only one critical point, we can define this functional, which I use now the capital lambda, and it is just the value of lambda in the critical point of the fiber. For example, if the function is like this would be TC, and then we are just computing this value here. Okay, so this functional is well defined, and it was called by Professor Iavidat the nonlinear generalized relay quotient. Right? So this is the so-called nonlinear generalized relay quotient. And by taking a look at this picture, in fact, we can prove this result here. So it lacks some kind of figure here, but you can believe that in fact this is true. So the Nehari set any lambda 0 can be completely understood by analyzing, by studying this relay, this nonlinear generalized relay quotient introduced by Iavidat. Okay, so now you pass from a function of phi lambda, which is the energy function, to this new functional which describes completely the behavior of the Nehari set depending on the parameter lambda. Okay, so just to mention, in this paper, Iavidat studied that functional, the lambda of u, which can be given explicit in terms of the Sobolev norm and LP norms and so on. And he defines this lambda star here by the infimum of this functional here. So lambda star is the infimum with u in the Sobolev space of lambda of u. And you see by this definition that if lambda is less than lambda star, so any zero lambda has to be empty. Right? So we reach to this point, and then we can find two solutions, one in any lambda plus and the other one in any lambda minus. Okay, so what happens before? So I start to study this relay quotient with Professor Iavidat in 2017, and first we were interested in try to understand how to generalize and how to apply these results in the regime or where this set was not empty, and then I realized that there were some energy functions for which this set was non-empty for all lambda. So for all lambda positive, there are some equations, some PDEs, and also some functions related to these PDEs for which this set here is non-empty for all lambda positive, and consequently we cannot apply the technique proposed by Yavidat. And so these works are related to this one. So for example, you can try to study some Schrödinger-Poisson equations or some Kirchhoff equations and so on. And in all of these papers here, we have a functional for which the Néhari set is not a manifold for all parameters lambda positive. Right? So we cannot apply the technique introduced by Yavidat. And how could we solve this problem? Right? How can we study these equations if by considering the functional restricted, for example, to the Néhari set, if the Néhari set is not a manifold? So I will try to explain this for you now, and just for you to have some examples in your mind, you can suppose that the functionals are these ones, right? So this is a functional associated to the Kirchhoff equation, and this is a functional associated to the Schrödinger-Poisson equation. This term here is called the Coulomb potential, right? So for example, critical points of this functional are solutions of an equation which has this form here. Okay, and this is a situation where any lambda 0 is always non-empty, and any lambda plus and any lambda minus are also always non-empty. Okay, so to fix ideas, let us consider now this functional. Right? And I will try to explain to you now how we deal with this problem. So since any lambda 0 is always non-empty, we can now, instead of understanding this equation, let us focus on this equation, right? So let us look for functions u in the Sobolev space, which has zero energy, right? So if you consider this equation, so you just put a 0 here, we can now isolate the parameter lambda, and you get from this a functional which is similar to this one here, and then you can prove that that new functional has fibers like this one here, and this is the TC for that function. And by taking this TC, you can define again this lambda, which is lambda of TCU, and this will give for us now this function which has this very nice expression. Okay, so what is the main idea to understand this function is that if lambda of u is equal lambda, if and only if phi lambda of u is equal 0. Okay, so if you want to understand the function of lambda, you have just to note that this is equivalent to say that u has zero energy for this function. In fact, not u, but the TC of u. Okay, so what can we say about this function? It is C1, which is clear, and this is the LP norm, this is the Sobolev norm, and this is the Coulomb potential. And it has this very nice property, which says that it's zero homogeneous, so lambda of Tu is equals lambda of u, and it's bounded from above. Okay. So this functional here, this follows from Sobolev inequality and so on. There is some constant C for which, for all in the Sobolev space, this is bounded by C. So if it's bounded from above, you can define now this extremal parameter, which is the supremum of lambda of U, and it has this geometric characterization, which is the following. If you take lambda bigger, lambda positive and small and less than lambda 0 star, then you can find some U for which the fiber associated to U, that is phi of lambda TU, it has a behavior like this. So it has a point with negative energy. However, if you take lambda bigger than lambda 0 star, every fiber of your energy functional has to be positive. And so you can have this case where you have a local maximizer and a local minimizer. So this point here belongs to N minus, and this point here belongs to N plus. Okay, and you can also have this case where this point is an inflection and it belongs to lambda 0. Okay? So this parameter is a threshold for this case here, the energy of our energy function. The energy in the sense of positive and negative and positive. And then we prove in all of these papers here that if you take lambda bigger than lambda 0 star, then you can find a global minimizer of your energy functional. So you can use just global minimization or Eklund. And this fiber suggests also a mountain pass geometry. And in fact, you can prove also a mountain pass solution. However, when you cross this threshold here, you can see easily that the infimum of your functional is now 0, right? Because every fiber is strictly positive, and so the infimum is attained at the origin. So you cannot do the same computation that you did before. Right? So to treat this case here, we have instead to look for local minimizers over the Nehari set in lambda plus. And if we are able to find this local minimizer, again, we can look for a mountain pass solution. Right? So in all of these papers here, we did this approach that I described here now. Okay, so what happens exactly when lambda is equal lambda 0 star, right? So if lambda is equals lambda 0 star, you have this very nice result here. So lambda 0 star, in fact, is the supremum of the functional lambda. And if U is the functional that attains the supremum, then you can prove that there exists some T positive for which T bar U has 0 energy for the functional at the parameter lambda 0 star. And moreover, it is also a critical point for this function, right? And conversely, you can prove that if V has 0 energy for this functional at this parameter, and it is also a critical point, then V is a supremum. So it is attained the supremum of lambda, and also is a critical point of the Rayleigh quotient. Right? So a picture for this, in fact, what we find here is a critical point for our energy functional with 0 energy. And if you picture the fiber associated to this solution, you can see that it has a local minimizer with 0 energy. Okay, so this was done. This was done by considering this equation. So you want to look for solutions of our functional with 0 energy. So instead of 0, if you put here some constant C, which may be positive or negative, so may we apply the same technique? So this is a question. So instead of considering 0 energy, can we consider some given energy and apply the same technique? So this is the main result of our work, and I will try to describe here to you again for this Schrödinger-Poisson energy function. So now instead of 0, we consider C, and again, a simple computation shows that this is equal C if and only if lambda is equals lambda of u, and here I put C as a parameter, where lambda C of u is given by this functional here, right? And you can now, again, fiber this functional, and I will fiber it only for C negative, although in our work we fiber it for C positive also. And the fibering of that functional for C negative is given by this graph here. Right? So for all C positive and for all U in your Sobolev space, the fiber always behave like this one. So it goes to minus infinity here, it goes to 0 here, and has a unique global minimizer at this point, which I will call now T of C and U, because depends of the energy C. And again, you can define the nonlinear generalized relay quotient by energy, which is in fact the value of the functional at the critical point T of CU. So here is T of CU at U. And what we know about this function? So one interesting property is that if C is equal to 0, right, we have this function again, which have this closed form, this explicit expression. But if C is negative, we do not have a explicit expression for this functional. But this is not a problem, because you can prove some good topological properties concerning it. So for example, this new function now, by considering C as a variable, so it is C1, right? For all C non-positive, it is, with respect to the second variable, it is 0 homogeneous. It is always positive and again bounded from below, right? And moreover, for all C non-positive, if U in our Sobolev space is a critical point of this functional, then similar to the last result, there exists some positive T for which phi of this functional at this parameter has energy C, and moreover, it is also a critical point, right? So in some sense, we transfer the problem of finding critical points of phi at some parameter lambda at the energy C to find critical points of this new functional lambda, which is the relay quotient. Okay, so now, in fact, what we want is to find critical points for this function. And to this end, we have to prove some more good topological properties. For example, it would be nice if this functional here satisfies the PS condition. Okay, and this is the case, right? And so since this functional is zero homogeneous, we all know that zero homogeneous functionals are completely understood by its restriction to the sphere. So we will define this functional to be sphere. Right? And since this one is bounded from above, instead of considering this one, I will consider its inverse, because its inverse now is bounded from below. Right? So this is the restriction of the inverse of this function over the sphere. And the fact is that this new function here satisfies all of these properties here, right? Is C1 is positive, is bounded from above now, and satisfies the PS condition. Okay, and moreover, the sphere is also a natural constraint for this functional, in the sense that critical points of this functional are also critical points of this functional here, right? And so if we find critical points for this functional, in the end we will find critical points for phi at some parameter lambda with some fixed energy C. Okay, right? So since now you know that this functional is C1, right? And it's also even, right? Because in this case here, this function is even, we can apply the Lusternik-Schirmer for this functional to produce the following result. So for all C non-positive, there exists a sequence of parameter. So this sequence depends of lambda, and it is a sequence on this variable. And the corresponding sequence, which I will call U and C, satisfying one. So by definition, by the explanation, this function here has energy C at this parameter, and it is also a critical point with respect to this parameter. Moreover, for each fixed n, this function here is continuous with respect to the variable C. It is non-decreasing and satisfies this limit. So when C converges to minus infinity, the parameter converges to 0. And for all fixed C non-positive, we have that the parameters that this sequence for fixed C converges to 0. Okay. And just a remark here, the case C equals 0 was treated in this work with Humberto and Jefferson. And this work, in fact, it motivated this work that I'm speaking about now. Okay. So just an observation here, this sequence is given by the method of Lusternik-Schirmer. So it is given by the supremum of the infimum of lambda tilde, right? Cu, where the supremum is taken over sets of category bigger than or equal to n. Okay, so let me try to explain this result with a picture. So in fact, by fixing n, you can assume that this is a real function defined on the axis C of energy. So the axis C is this one. And then we can plot the graph of this function. And these blue curves here are in fact the graph of the function lambda n, lambda 2, lambda 1. So this is the first one, right? So when C goes up, lambda goes to the left because this functional is non-decreasing. So this is the second curve. This is the NF, and the curve for n. Okay. So each curve in fact gives us a solution. So for example, if you fix a point here, you are saying that you have a solution for your functional with that energy, right, equals C, and it is a critical point of your function. Let us call, for example, this U. Okay. So in fact, we find here a sequence of curves. Each one gives solutions of our PDEs with some prescribed energy C. Okay, to be more precise, our result does not exclude these pictures here. So what does these pictures mean? These pictures means that, for example, one curve could cross another one, which is the case when the critical energy given by the Lusternik-Schirmer are equal. So for example, you could have something like this, lambda n C equals lambda n plus 1C. And this equality implies that these curves intersect. This case here is because we only prove that this functional is non-decreasing. Right? So to have a picture like this, we should have proved that this function in fact is increasing. So if it is increasing, the curve is like this. But if it's non-increasing, it could happen that there are some vertical segments on the graph of the functional lambda. Okay, so by analyzing that picture, we can also prove as a corollary of our theorem that So just by looking at the picture, right? You draw this vertical line here, and you see that this vertical line, so if lambda is less than lambda n 0, you see that this vertical line, it crosses at least n curves. So in fact, if it crosses at least n curves, we are proving that we can find at least n solutions with negative energy. Okay, so one might question, well, what happens if the curve is like this, or if the curve is like this? Well, if the curve is like this, you could have something like this. So in fact, you have infinitely many solutions. And if the curve is like this, we know by Lusternik-Schirrmann that at the cross, that at the intersection, in fact, we have infinite solutions also. So in any case, we can prove that we have at least any solutions for your PDE or any critical points for your energy functional for this fixed parameter and with negative energy. So just to finish now, let me describe this same result in its full generality, right? So we prove more than this last picture, and in fact, we prove this picture here, okay? So concerning solutions for lambda positive, we prove the existence of infinitely many curves, right? Which goes from minus infinity to this value here, C star. So this is the first one, the second one, and so on. And also we prove this is the existence of another sequence of curves, which comes here from minus infinity, and also stop at this level C star. So in fact, the theorem showed the existence of infinitely many curves of solutions with prescribed energy for our function. And from the picture, you see again the same feature. So n solutions with negative energy. And from these blue curves, we see that we can also find n solutions with positive energy. Okay. So I believe that both of these results here are new for the Schrödinger-Poisson equation. And in fact, our work it concerns not only the Schrödinger-Poisson equation, but many kinds of equations and energy functionals. So just a picture concerning the concave-convex functional. So for the concave-convex functional, we proved that this result here. So infinitely many blue curves coming from infinity and stopping at this negative level C star. Infinite many curves, red curves coming from 0 and stopping also at C star. And from this picture, we see that if you draw this orange line here, this orange line will cross infinitely many curves, right? So this shows that there exists infinitely many solutions with positive energy. And in fact, it shows more. It shows that lambda infinite, lambda here, is a bifurcation point for this equation in the classical sense. And concerning the red ones, if you draw this green line here, we see that it crosses infinitely many red curves, right? So in fact, we proved that there exist infinite many solutions with negative energy, and in fact, this point here is a bifurcation point in the classical sense. Okay. And now, so some related works, some results that exist in the literature and has something similar to these results. So for example, if you take this work by Binding and Ouyang, which considers this equation, so for simplicity, you can assume here that m is 0, and this is 0, and this is, for example, a superlinear term, right? So in this work here, Binding and Ouyang proved something similar to our results. So they proved the existence of infinitely many solutions like this with positive energy, and they converge here to the eigenvalues of the P Laplacian operator. And our result also captures this case here in a more general abstract way. Another comparison is this work of Barth and Mandel for the concave-convex nonlinearity. In this work here, they assume that omega is an annulus and that U is radial, and they prove the existence. This picture here is with respect to lambda and the C1 norm, but it can compare to our picture, right? So they prove the existence of infinitely many curves. And if you compare this picture with this one here, you see that the blues correspond to this part here. Unfortunately, we could not connect the curves, right? And the red ones are these down here. Okay, so our work it can be applied for more general domains, and so in some sense it captures also this result here. I put this new result here, which was published in the archive by Yavdat, and where he considered this technique in some abstract sense and apply it to analyze at least the ground states, or at least the first curve here. This curve here is in fact a curve of ground states for this functional restricted to 20 plus, and this first curve here is a curve of ground states to our functional restricted to n minus. And just a glimpse of some equations are where our work can be applied. So some Ouyang equations and Lane-Enden equations. So the concave-convex, Kirchhoff equations, Schrödinger-Poisson, or Odinger-Bopp-Podolsky, and so on. Okay. And that's it. Thank you. I apologize for the English. I know that's bad, but I believe that I could present everything to you. So thank you.
Thank you very much, Kaye, for the beautiful talk. It was very nice. In the audience, do you have questions or comments?
I have a question. Can you hear me?
Yes.
Okay. Many thanks, Kaye, by nice talk.
Thank you.
So I have two naive questions actually. The first one is when you consider applications, you always consider powers that are below the critical power, right?
Yes.
Okay, so even with the new techniques, there is nothing to do with that. I mean, can you go a little bit further than that?
Yes, part? Yes. There are some difficulties, as you know, for example, with compactness. But for example, in this work here, with Francesca Faracci, it's not the same approach. It's something different, but we use here the Néharic manifold and the idea proposed by Yavdat. And here the problem is critical. Okay. So the problem is critical, and there are some very nice difference and very nice new features. So yes, we can try to apply this technique to critical or supercritical problems too.
Okay. Okay, I see. So my second question is related to when you consider the Schrödinger, I don't remember the second name, Poisson. If you can show, please, the equation.
This one?
Yes. So my problem is related with imagine that your functional has no, I mean, it has a space dependent function in front of the phi u square. It is that important in your theory, or you can consider, I mean, you can consider phi of u square, or you can change that by a function k of x times that function.
Yes, let me just
I mean, I'm saying that because I don't know. I mean, you have a Schrodinger Poisson, but other people say we consider another kernel that has not exactly the same structure as Schrodinger Poisson.
yes, you can consider more general operators here if you want, and there are lots of papers on this. And also you can consider a more general functional here too. For example, some f of u. In our work, I mean, you can study this kind of equations with more generality, but our approach does not deal with this kind of generality.
Okay, perfect.
But yes,
Okay.
it's possible. It's possible to study this Schrodinger-Poisson equation with more general terms. Here too, you can consider some g of u. But you see, this equation, it has many applications in
Yeah,
physics.
I know.
It has a lot of open problems related to it and so on.
Okay, thank you so much.
Thank you, Paul.
What is the role of the dimension n equals 3?
Because of physical applications. Just because that. There are papers which study this problem for n, for example, a dimension n, but in general they are not so well accepted because they have no physical application. So mathematicians tend to study this problem for R3. This one and the Kirchhoff also.
But you have an idea if the method applies as well?
Yes, it applies. It applies. You can consider this equation. Maybe you have to make some changes here, I don't know, but yes, you can consider this equation for n, and the method can be applied with no problem. For example, Gaetano, which studies this equation a lot, he said me that in general people don't like to study it in Rn, so I believe him.
Okay. Do you have other questions or comments? And I can see actually I cannot see very well the role of the domain, because you said that if you change by annulus, then it changes completely the geometry of the fibers, right?
No, the fiber not.
But the lambda one, the cure,
Ask again, please.
I think it's the 1-2 slides from this one, maybe the work that you are saying about the annulus.
Okay.
Because they intersect, right? The red ones and the blue ones, yes. They kind of intersect, and they become one thing.
Yes.
But
yeah, so I believe because since you are considering this equation in an annulus, you can transform this equation in an ordinary differential equation, right? And use techniques. I believe that this is what they do here. Maybe I'm speaking nonsense, but I believe that what this is their technique. They transform this equation in an ODE and use techniques related to ordinary differential equations. And so by using these techniques, they can connect both curves. In our approach, since we have to deal with the Néhari manifold, we are not able to connect those curves. So you see here that the blue curve come here and the red curve come here. They do not connect. So it is our dream, and this is an open problem, to connect both curves. So we believe that we can now extend both curves and they reconnect down here. So this is in some sense hard because this parameter C star is the threshold for the application of the Néhari method, in the sense that after this parameter, we have that any zero is non-empty. So all of our technique here cannot be applied, at least in a straightforward way, for C bigger than C, less than C star. So in some sense, our approach deals with more general domains. So here you can take any dimension n and n and omega to be a bounded open set. However, we lost here since we cannot connect these curves.
Okay. So if we don't have other questions or comments, I will thank our speaker again, and thank you very much. I'm not trying to. Okay. And thank you very much. I will stop.